Greetings, everyone. So we're going to continue with our volume discussion, but we're going to form the solids differently this time than we did in the last video, where I told you that there was a certain shape to the cross-section, and that the region that we were talking about bounding the base sat in the XY plane. Here, we're going to be revolving that region around an axis of revolution. So as it says here, I want you to imagine the region bounded by y equals the square root of x, the x-axis, and the lines x equals 2 and x equals 9 is revolved about the x-axis. So we're going to spin this around the x-axis. So imagine, you're taking maybe a sheet of cardboard or something right here, attaching it to some axis, and you start spinning it really quickly around that axis. What's the volume of the solid form? Well, I guess the first question is, can you imagine it? Okay, because that's a big part of this. Actually, it's not that big of a part, but it can be helpful. Now, I'll remind you, and I'll give you a visual animation of this in just a moment, but I want to remind you that what we said in the last video still applies here. Our key to these volume problems is that we want to integrate the area of the cross-section from the endpoints of the interval here. So I'm still going to do that. I just got to figure out the shape of the cross-section that is formed when we do this revolution. So to visualize this, before I actually give you the animation, I want you to imagine that your face is right over here. Actually, I want the side of your head over here. So your eye is over here, you're looking over here, here's your ear, and you're looking in this way. And this thing is getting revolved, so it's going to be projected down over here also as it's getting revolved like this. And it's spinning really, really fast, so it looks like a solid. I do want you to imagine the typical slice like we do. What does that slice look like when we revolve it around the x-axis? All right, well, let's switch to a different screen here, and let's take a look. There's a more accurate picture here of this. So let's revolve that one rectangle. So now again, imagine that your eye level is right here along the x-axis and you're looking inward. What shape are you going to see right here? That shape that you see is the shape of the cross-section. And again, the key to these volume problems, the way we're handling them, is that we want to integrate the area of the cross-section in order to get the volume of the solid. So have you determined the shape of the cross-section? Hopefully you have. Hopefully you can visualize that the shape that you're looking at when we revolve this is just a circle. Now I got to draw it a little bit elongated. It's going to look more like an ellipse because of the perspective from where I'm drawing it. But the shape of the cross-section is a circle here. It's just a circle. And how do we find the area of a circle? Of course, the area of a circle is pi times the square of the radius. So we just got to identify the radius. Now, if I'm looking at this picture and carefully noting, these are opposite ends here of the circle. The center of the circle is going to go through this axis of revolution. So the radius is just from the axis up to this edge right here, or where this rectangle hits. What is this length? Well, that's just the square root of x. And so the area of my cross-section here is just pi times the square root of x quantity squared. Now I got the volume. The volume is just the integral. What are my limits of integration? Well, I'm doing this from 2 to 9, so those have to be my boundaries. Those are my upper and lower limits of integration. The area of the cross-section is just pi times the square root of x squared. We could simplify that, but I'm just leaving it like this for effect. And then I got to close my parenthesis. I got to put my dx down there. And that integral is going to give us the volume of this solid. Let's go take a quick look back over here for a moment. Let me show you more rectangles. With 5 slices in this picture here, you know, I was to revolve all of them, it would look like this. But that's not very smooth because, you know, I'm only taking 5 slices. If I could change the number of slices here to, say, 50, and what do I want to do? Idle original rectangles, show the rectangles. Actually, I think I need to reset this so it looks a little bit better. Now, notice how skinny this looks here. If I show all the rectangles, you can't even really tell them apart. There's 50 of them there. They look like they're blending together. If I revolve just the one, it's a very skinny, almost cylinder. It's not quite a cylinder because the 2 circles on either end are not identical to each other, because the one closer to or further to the left has a slightly smaller radius, but that's okay. And if I was to see them all like this, you can see it looks like a smoother figure now. It's got a little bit of a jagged edge to it, just hard to see. So that's what this figure looks like. But to find the volume is rather easy because it's the same thing as before, finding the area of the cross-section. And because we're revolving this around an axis, this is a circular cross-section. You can find the area of a circle. You've been doing that since middle school, maybe earlier. And we can find, once we find that area of the cross-section, we can write the integral rather quickly. Now, there's a key thing I want to point out here in these types of problems. Let's go back to the 5 rectangular case, and then I'm going to reset all of this. I want you to notice that the rectangle that we drew here has its bottom edge on the axis of revolution. In fact, all the rectangles that I could possibly draw, no matter how skinny or how wide to do the approximations, they all have an edge on the axis of revolution. That's important to notice. That means there's no gap in between these rectangles and the axis of revolution. And when we revolve them around these rectangles, we revolve them around this axis, we get a solid circle. But what if we move the axis of revolution but didn't change the area? Maybe our axis of revolution is down here at y equals -3. Now notice, when the axis is down here, y equals -3, this rectangle's edge, neither of them, no longer touches the axis of revolution. None of them do. But more importantly, if any one of them doesn't, I've got a problem. The cross-section is no longer a solid circle. It's different. Let's revolve that one rectangle and take a look. Now, if you notice in this example here, we have a small circle in here. This would be hollow. We would be able to, if this was like a vase or something like that, well, this vase would have a hole in it. So it wouldn't hold any water, okay, because of this inner circle. This outer circle and its thickness would form the vase itself. I don't have a better word for it at the moment, so I'm just using vase. But because of this inner circle here, that's hollow, that's empty, we would end up with, you know, an open space through here. So it's no longer a solid circle. So if my problem is changed, I'm going to do a very quick sketch here, and it's probably a very poor one, but just so I can point to some things. So here's the graph. This is the region. This is 2 and 9. And this is -3, just pretend. And I want to do some measuring here. So I still draw my rectangle. You should still draw your representative slice. Okay. Now again, we're not looking at a solid circle as our cross section. Our cross section is a circle with another circle cut out of it. I'm pausing for a moment. I'm going to go back up here. This example that I first gave you for this, where we have a solid circle. This has a name. It's called the disk method, because the solid circle has another name. It's called a disk. Okay. Technically, the circle is the set of all points, locus of all points that are equidistant from some fixed point. The circle is these points around here. The inside of the circle, most of the time, under most cases, is not considered to be part of the circle. There are some exceptions to that, and there's some debate about that in certain cases, but the solid circle, including its inner area, more generally we like to call a disk. At least we're going to do that for this one. Down here, when we have a circle with the circle cut out, the method we call this is called the washer method. If you've ever been into a garage or a machine shop or something like that, you get a screw and some sort of screw. It's got this. It's grooves on there to screw into place. Well, oftentimes you put a washer down first for the screw because the washer provides support so that the screw head doesn't pull through the sheet metal or whatever it is it's going for. It spreads out the force of the head of the screw or the bolt. Anyways, I'm getting into too many details there of the physics. That's not important. What's important is that this thing's called a washer, and this is called the washer method. Okay, it kind of looks like a donut, but it's flat, so it's not really a donut. And so we call this the washer method. Now, to find the area of a washer, it's not that hard. I have two circles, one with an outer radius and one with an inner radius. And basically, I just need to take the area of the big circle and subtract from it the area of the small circle. And that'll be the area of the cross section. And then we'll apply it over here in just a moment. So the area of the big is going to be pi times let's call this cross section here. So the area of the cross section is going to be pi times radius r sub 1 squared, since that's what I called the bigger one, minus pi times r sub 2 squared. Now, mathematicians don't usually leave it this way, and you'll see it a little bit factored out. They factor out pi, and we often do that in our formula I'm going to give you here in a little bit. So it looks like this. Now, this is the square of the outer radius, the bigger one, minus the square of the inner radius, the smaller one. Okay. Now, this is what I need to find the area of the cross section. I need a bigger radius, and then a smaller radius. And then I plug them into this formula, and then I plug them into the integral. Where do I get those radii from? Radii, plural of radius, if you've forgotten. Well, if you go back to this picture over here, the axis of revolution goes right through the center of these two concentric circles. And so I need to measure how far away the edge is. If you imagine a rectangle existing right here, okay, the inner radius is the closer edge of the rectangle to the axis of revolution. The outer radius, R1 here, is along here, where to the outer slice, okay? So here's our slice, the rectangle you saw. The edge of the rectangle that's closer to the axis of revolution, that's this length right here, this is the smaller radius, the inner radius. The edge that's further away, that's this one up here, its distance from the axis of revolution, that's the larger radius, okay, because that one's obviously further away. That's r sub 1. How do I calculate these things? Top minus bottom. The rectangle's vertical. We're doing this with respect to x. As we did in earlier sections and other examples, top minus bottom. What's the top function? Here, the top function is the square root of x. What's the bottom function? Well, I get all the way down to here. The bottom function is your y equals negative 3. So it's going to be top minus bottom. What about this closer edge over here? What's the top function? Well, it's on the x-axis, so that's, if we remember, that's y equals 0, so that's 0. What's the bottom function? It's that negative 3 again, so minus negative 3. There's my inner radius. And so the area of the cross section is pi, because we're rotating, times the outer radius squared. Now I'm going to simplify, I'm going to simplify this a little bit so I don't have minus the negative. I'm going to have a plus 3 here. Squared, so root x plus 3 squared. That's my bigger radius. Minus my smaller radius is just 3. 0 minus negative 3 is 3. So that's not cubed. That should be squared. And then I got to find, I got to take the integral to find the volume. And we're doing this from 2 to 9 still. You could put the pi here, or you could put the pi out in front. It's your choice. It's the same thing mathematically as we've talked about way back in section 5.2. If you want to square the 9, you can, or you can leave it as 3 squared. It does not matter. Just if you square this piece, I don't recommend that you do. Make sure you square it properly, because it's not just root x squared, which is x plus 9. You got a middle term here if you do a generic rectangle. Please don't make that mistake. We talked about that way back in the beginning of the year. Some students make that mistake. Please don't let that be you. And that's it. We have a disk method and a washer method. The hardest part is identifying your radii. I'm going to post some other videos that's going to walk you through some of that stuff. So I'm going to keep this video short and just make this introduction. So you want to identify your situation as either the disk method or the washer method. Use the appropriate area formula for the cross section, then write your integral, and you're good to go. You're going to want to practice this, ladies and gentlemen. Just watching me do it is not good enough. Check out the other videos, then go practice, 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 and go study.